Hi everyone, this is Miss Moore and today we are learning how to graph linear equations using information from the equation itself to generate the graph and going backwards using information from the graph to create linear equations. If you don't have the lesson template in front of you, please grab a sheet of lined paper or graph paper or just a notebook to take your notes for today's lesson. Last time we learned that linear equations are one way of representing a linear relation, a relationship between two variables where a constant change in one variable produces a constant change in the other. Now, throughout this unit, we've seen linear equations in various forms, but the most common form that's used as a template or building block is y equals mx plus b, where y is the dependent variable x is the independent variable, m is the slope or rate of change, and b is the y-intercept. Up until now, we've been saying rate of change instead of slope, but these are the same thing. And how do we calculate the slope? M is given by the change in y over the change in x, which is the change in y value between 2 points divided by the change in x value compared by the same 2 points. This is commonly abbreviated as rise over run, and you'll see why in a minute when we start exploring the graphs. There are two ways that we can graph a linear equation. The first, method 1, involves creating a table of values and then plotting each coordinate. Let's see an example. A linear relation has the equation y equals negative 3x plus 6. Create a table of values for this relation from x equals negative 3 to x equals positive 3 and then graph it. In our first column goes the independent variable, which is x. And in our second column goes the dependent variable, which is y. Now we're supposed to graph this from x equals negative 3 all the way to positive 3. So we'll start by filling in all of our x values. And then we can calculate the corresponding y values using the equation. Each y value is equal to negative 3 times the x value plus 6. Our first x value is negative 3. So negative 3 times negative 3 plus 6 equals 15. We can repeat this process for the remaining entries in the table. Negative 3 times negative 2 plus 6 equals 12. If we continue, we'll have a value of negative 1 pairing with 9, 0 with 6, 1 with 3, 2 with 0, and 3 with negative 3. Now the only way that we're going to fit all or even most of these points on our graph is if we scale it such that 1 unit on the graph is worth more than just 1 unit. So what I recommend is taking a careful look at the span or the range of your different values to determine what kind of scaling you need to do for everything to fit. X is just going to go from negative 3 to positive 3. So we can use a one-to-one scale for that, no problem. Now you don't actually have to label each one. You don't have to go 1, 2, 3, 4, 5, 6. That ends up being pretty crowded when you start putting points on your graph. So if we are using a one-to-one scale, I recommend labeling it at increments like 2, 4, and 6, for example. So that'll fit our x values no problem, but our y values range from 15 to -3. Now, squeezing them all on there might be a little difficult, but let's just try and get most of them on there by choosing a scale factor like 2 for our y-axis. So if each unit becomes 2 instead of 1, then we'll have 2, 4, 6, 8, 10, 12. To plot our points, recall that coordinates are plotted in the form x, comma, y. So if we start with the y-intercept, for example, this is at an x coordinate of 0 and a y coordinate of 6. Next we could do 1 comma 3, and then we could do 2 comma 0, and -1 comma 9, and so on until you see the pattern that these coordinates are forming, and you can grab your ruler and draw a straight line through them. So the question asked us, should we connect the points? Explain. Relations are always considered continuous, meaning that we do connect the points, unless the circumstances or the scenario from which the equation arises does not have in-between values. So down here I'm going to say this relation is continuous. So we do connect the points. Continuous means that there are in-between values. For example, is there a value of x in between 0 and -1? Yes, there are many. There's -0.5, -0.5, -0.2, -0.0000567. There's infinite values pretty much in between those 2 points. So therefore, we connect the lines. Now, in different situations, when we have more context for the situation that our equation represents, like how many pairs of shoes can you buy, um, there are in-between values for money, but there are not in-between values for pairs of shoes. So both of your variables have to have in-between values for you to connect the points. If they don't, it's called a discrete relation. So on the top of the next page here, let's make a summary of that theory. Continuous relations have values in between the data points. Discrete relations do not. Second way of graphing a linear equation is to use the information embedded in the equation, including the slope and the y-intercept. So say we had the equation y equals 2/3 x plus 1. Graph this relation using the data only from the equation. So first we identify our slope, which is 2/3, or 2/3. That means that our rise is 2 and our run is 3. Let's translate that into terms that we can understand for our graph. This means that we go 2 units up for every 3 units to the right. The second piece of information that we have is the y-intercept, which is 1. This means that the point 0, 1 is on the graph. Go ahead and draw your axes. And I usually recommend plotting your y-intercept first. Here's the point 0, 1. Now you can use that coordinate as a jumping off point to count out your slope and generate additional points on this graph. Our slope is 2 units up for every 3 units to the right. So to count out our slope, it's going to look like this. 1, 2, 1, 2, 3. Here's our next point on the graph. Use that to count out the next point. 1, 2, 1, 2, 3. And you can also count backwards to generate points in the other direction. The opposite of 2 units up and 3 units right is 2 units down and 3 units left. Now I'm going to erase all these ugly lines that showed my counting. You do not need to include those. That was just to show you where all of our points are coming from. Now grab your ruler and connect the points. Should we connect the points? Explain. Well, just like our previous equation, there was no context which led us to believe that there would not be in-between values. So whenever there's no context, we assume that there are in-between values. So we say this relation is continuous. So we connect the points. In example 3, we have a skydiver dropping from a moving plane 40,000 meters above the ground. The skydiver falls at a rate of 5,000 meters per minute. Please try this example on your own, pausing the video here while you do it. Okay, so here's my table of values, and I used it to determine my rate of change, or my slope, which is calculated by the change in y value, or in this case, height, divided by the change in x value, or in this case, time. What would that look like? For us, negative 5,000 divided by 1 is our slope, or our rate of change, which we need when we're building the linear equation. M equals negative 5,000. To build our equation, we also need to replace y and x with our dependent and independent variables h and t. Just a reminder that when you're solving problems in context like this one, you need to be careful of the difference between a quantity and a unit. So the quantity is like time, and the unit is the measurement of that quantity, so minutes. Or in the case of height, the unit is meters. When you're solving problems, whether it's in math or science, you need to use symbols that represent the quantity, like T for time, not M for minute. Likewise, you cannot use M to represent height in meters. You need to use H for height, and then meters is the unit of measure. We do not want confusion between quantities and units. So we always choose our symbols for each variable based on the quantity, not the unit. Also, don't forget that this is the position for our independent variable, and therefore this is the position for our dependent variable in our table. So you have to figure out which depends on which. In this case, height depends on time. So when I graph this relation, I use the y-intercept as my starting point, 40,000 meters above the ground, and then I counted out my slope. I go 5,000 meters down for every 1 unit of time that I move to the right, which led me to produce the following points on my graph. And we do connect the points because this is a continuous relation. You can be 22,547.656 meters above the ground, and you can be 4.557 minutes into your fall. There are in-between values for both quantities. In the last part of today's lesson, we're going to look at the difference between horizontal and vertical lines and how to write equations that represent them. Let's look at this example here. Y equals -4. What does this mean? It means that at all points in the graph, y equals -4. So if I count down to -4 on my y-axis here, y equals -4 at x equals 0, and x equals 1, and x equals 2, and so on. Every single point on the graph has a y value of -4. So this is what our graph would look like. What kind of line is this? Horizontal. Likewise, if we were asked to graph x equals 3, it means that at every point on this graph, x equals 3. So x equals 3 here, and here, and here, and here. Every single y value produces an x value of 3. What kind of line do we have? Vertical. So the trick here is remembering what y equals -4 or y equals b really means. It means every point on the graph has that y value, so it must be producing a horizontal line. Or in the case of x equals 3, or in general x equals a, every point on the graph has an x value of a. Please try example 4 on your own and pause the video here while you do it. A little hint for you, you're going to need some algebra to make this look like y equals mx plus b. Okay, let's compare our graphs. Y equals 3 is a horizontal line. Every point on the graph has a y value of 3. Y equals 3x produces a slanted line, and if we compare that to y equals mx plus b, we see that we have a y-intercept of 0 and a slope of 3 over 1, which is how I was able to count out all those points on my graph. And finally, we need some algebra for y minus 1 equals 3x, which I have down here. You have to rearrange this equation so that it's in the form y equals mx plus b, and you can identify your y-intercept and your slope. Our y-intercept is 1, and our slope is 3. So you can start by graphing your y-intercept and then counting out your slope. Okay, everyone, it's time for your assignment. Please don't forget to check your solutions before handing it in. Bye for now.